my voice, so if you make a lot of noise when you crank it up to hear me or to hear you, scratching your head. So scratch your head if you need to, but try to not to. Okay, so I have a couple of comments about the problem solving session yesterday. Please don't get discouraged because no one solved a large number of problems. It's to be expected because, well, of course, there are only hard problems, maybe even only really hard problems. So the idea, as I told you yesterday, was that you test your ability or you train your ability to endure through a problem. Right? So if you take a problem that takes a long time to solve, that means, I know, many details will be working the paper and maybe longer code, than the first or second problem you are used to solve. So for the project you didn't get to solve during the contest, or even if teammates solved it and you didn't, you can use them to train this at home or here on your free time. So, but in order for that to work, you have to solve it in a maybe different way than you are used to solve problems on your own. So it's important that you sit down to solve the problem, either individually or as a team, and you solve it all consecutively without distraction. I mean, I know that for problems outside the contest simulation, sometimes one reads the problem and thinks about it while doing something else, or maybe think about it for a day and then works out the details slowly in your head, and then you start programming and maybe you stop and go do something else and come back to keep programming. So it's a completely different context as solving during a contest. So that's fine for some problems. I mean, especially problems that use techniques that are new to you. It's good to do this kind of solving it through an entire day or something like this, because this makes all the ideas fit perfectly in your head. But this doesn't really have two new techniques for you. It should be things that you already know, maybe are hard to combine or hard to work out. But so really, if you solve it like this, it kind of misses the point of this kind of problem. So I would suggest that you I know, instead of you take an hour or 2 hours or whatever time you have and try to solve 1 or 2 of these problems as if you were in a contest. So all consecutively, kind of in a little bit of a hurry, trying to solve it as fast as possible. Okay? Because there are a lot of good problems. And for today, instead of going through all the solutions for all the problems, since that will take a really long time and maybe not be so useful, what I think about doing is we're going to go through some of the problems and but work them out in detail. Okay, so I can tell you maybe some tricks or some ideas that may be related to this specific problem, or maybe okay, this is also useful for something else, but that may be useful to you in other problems. Because of this kind of problem, I mean, just working out the problem in the board is not going to help you very much, and it's going to miss the point of, okay, I have to do this thing where I get the problem and I think, and I solve it all together. So I'm going to be solving some of the problems depending on the time, on how many questions you have or whatever, maybe more or less. And the rest are going to get unsolved. You can ask me about the problems that I didn't solve on the board today during lunch or in any intermediate time if you want. And also I'm going to be solving the problems that were less solved during the contest. So maybe for the others you can also find some other of you that knows the solution because the team already solved it in the contest. So you can also ask your, I don't know, classmates, I don't know how to call it. Okay, some of the other teams. Okay, that's all the initial comments. So I will begin with the first problem, the local language problem, which is one of the most hated problems I remember. So one thing solved it with the comments. Is anyone here? Is anyone? You solved it. Okay. So what do you do?
We use the segment tree with basic propagation.
Okay. Yes?
explain how I did it?
Yeah, I would like that, but I'm afraid maybe a little too long if you explain and then I explain what I want. So yeah, so I'm going to more or less explain the problem, but I'm going to put more focus on explaining how this, like what I think are good ideas how to implement this lazy update technique on segment trees, and in particular for this problem. Okay? So because it's better for you to hear about the structure and how to use it, because this problem is already old. You need to understand how to best use this for your problem. So don't worry, you will get the chance to speak tomorrow. Okay. So we have the segment tree. The segment tree, we usually have an array where we have some values that are tied to the problem. Like I know for the range query, standard problem, we have here some values. And then on top of this, we build the tree. And then in the internal nodes of the tree, we decide, okay, we are going to store some data, which usually we calculate the data recursively from the node below. And this data represents something about the range of all the range of the array that is directly below the node. So this node right here represents this subarray, this number here represents this subarray, and so on and so forth. Okay? So each node represents exactly the union of its two childs. Or maybe one child, if we are depending on exactly how we do the tree, we allow things like this, we may have one or two childs. In the union of all its childs. One or two or three. Okay? So we can also think of these values as data and say, okay, every node of the tree has data, and the difference is that the invariant for the internal nodes is something about the childs, and the invariant for the leaves is something about the problem. Okay? But the internal nodes generally do not have anything to do with the problem. Okay? So you all at least program this once. Let's use a segment tree at least for range query operations. Okay. So when we have a query of this sort of structure, we are given some range. Then we split this range into maximal intervals that are represented by nodes. Okay? There are several ways to do this. One is bottom up and one is top down. I prefer top down because it's easier to implement. So what I usually do to implement this is I remember in each node what is the range of the array that is represented. Okay? This is also good because you can do this kind of thing where some nodes do not represent a fixed length array. So I don't know. So this node will store something like 0, 2. This will be something like 2, 4, 4, 6. This will be 6, 7. Okay? And I write like this because it's closed on the left and open on the right because it's easier for computers to process this kind of thing. But you can write it wherever way you feel more comfortable. And then of course this is going to have the right end here and the left end from this node and the right end from this node, and this is going to have the left end from this node. So these are all pretty easy to calculate on the fly if you want, but having them pre-calculated makes it easier for the code. Okay, so in the structure or wherever we represent the nodes, we store these values. Besides the data we want to store. Okay, so then when some query comes, we ask the root for the query. So suppose we are asking for a range, I don't know, let's say 1. 1, 6. Okay? So first we ask the root. I'm saying we ask the root because I'm thinking about the recursive implementation like the try I showed yesterday. in which usually the nodes have the operations on the operation, and when you ask the node an operation, the node can do one of 2 or 3 things. It can solve some part of the operation, or it can ask one of its childs or both to solve the operation. Remember yesterday we said, well, we are going to insert, then we decide one of the childs and we insert in the child. Or if it was the empty string, we insert on ourselves. Okay? When node receives an operation. Now what we're going to do is say, okay, we're going to split this query between the childs of the node. Okay? So here the root is this. And so the root is representing some interval, and we receive some interval. Well, in the case of the root, there are not that many possibilities. The interval has to be inside. Otherwise, we're asking for values that do not exist in an array. But in general, there are a couple of things that can happen. The interval that we are requesting can be, I mean, the invariant we're going to use is that the interval is always inside the interval we are representing. So we're not going to ask any node about values that the node doesn't know. Okay? So we are not going to be asking this node about the values 5 to 7. And so on. Okay? So here is fine because we have 1, 6 here. Here. And we have 0, 7, which is the range of the root. And we know that the root knows because we can ask any of its childs that they are split by the number 4. Okay? So we have one of the childs covering the range up to 4, and the other, and the right child covering from 4 to the end. Okay? So there are 4 situations that we have to distinguish. One is that we are asked for the entire range. Okay? If that's the case, that means we can answer directly. Okay? Because that's what we do in some instances, right? We remember the result for the query. So if we are asked for exactly the range of the current node, then we return directly without doing any further search. If the range we are requested is completely inside one of our childs, right? We just ask the child, either left or right. So basically, if 4 is not inside, in this case 4 is not inside the range we are requested, then we know one of our childs contains the whole range that we're being queried. Okay? So we do a comparison, and then ask the appropriate child for the result, and that's it. And let's say the only complicated case is when the range is like this, when we have a little bit on the left and a little bit on the right. If this happens, what we do is we split the range into 2, exactly at 4. So we say, okay, so 1, 6 is 1, 4, 4, 6. And then we ask this to the left, this to the right. And when we get the values back, we combine them, and if it's minimum or maximum, we're just taking the min or max, and maybe some more complicated problem, maybe some more complicated operation, but the idea of the segment tree is that we can combine the sub-results into one result. Right? This is an invariant that has to happen for the segment trees to apply to a problem. Okay, so we will ask 1, 4 to the left, and 4, 6 to the right, and forget it. Okay, and the good thing is that it's pretty easy to see that this works. Right? We don't have to make extra considerations. The only hard thing, a little harder thing to see is that why this works that fast. Right? Because since we have an operation that asks both childs what do they think about this, then it may seem at first sight that we may be asking all the nodes in the tree, and then we are not really doing something logarithmic but linear. But what happens is that once you split an interval, the interval, when you request an interval that has one of its ends exactly at the end of the interval that is covered by the node, so for instance, we will be asking the left child of the root for the interval, in this case 1, 4. Okay? So from now, every time I split this interval again, the right part is going to be exactly a whole node. Okay? Because if I split it, I'm going to split it in the middle. So since this edge is already exactly this edge, if I split, the right part is going to be exactly the 9 nodes, so it's not going to propagate splitting all the way down. And the same happens with the left part with this left part for splitting to the left. Okay, so this interval right here can go either left or right, but if it splits, it's going to be that splitting only is only going to propagate to the left. Okay, so we are really going to cover 2 branches of the entire tree. Okay, so the entire query is going to process nodes in something like this fashion. Maybe some of the nodes may have a single node dumping to the right. So the left branch from the root may have some query to the right, but only one, only of left one. Okay, because when we do this kind of zigzag thing, then we cannot split this again. And the same thing happens to the other side. So basically, since the 2 branches have the logarithmic height because it's the height of the tree, and then as we have at most 1 extra node per each node in the branch, we have at most 1 extra node to the incorrect side, let's say. Then we have at most 4 log n, so 4 times the height of the tree number of nodes involved in the entire query. Okay. But here it discusses all the difficulty in the proof, but in the implementation it's really easy. It's like you do the intuitive thing to do with the internet. Okay? And this also makes it really easy to adapt the structure to some new usage. Right? Because you can do the same trick as we saw yesterday in the try, because what you say is, okay, every time I go through a node, then after I do whatever operation I'm requesting, I recalculate the value recursively on the values of the charts. Okay, so if this is, I know, minimum range minimum query, after I do some operation that alters the structure, I ask both my child from their minimum, I compute the minimum, and I restore the value. So it's the same as we were talking about yesterday with the try. Okay, so this is the regular segment. So lazy propagation or lazy update or delayed update means that instead of saying, okay, so for updating, what we usually do is changing the value in the original array and then going up in each branch, updating the values of all the nodes. So basically we will, alter this value and then go to the parent node and say, update yourself. Then say to this node, update yourself, and say to this node, update yourself. Okay? In general, for minimum or maximum or sum or this kind of easy operations, sometimes we know how to update without needing for the node itself to. So if it's maximum, we know that we just need to take the maximum of the current value and new value. But the easiest way to do it is just to ask the node to recalculate its own value, and so we calculate it every time in the same way. So we have the same way to calculate if we are going down with some update or up. So this is the regular update that takes logarithmic time in a segment tree, but it only allows us to update one position at a time. Right? So lazy propagation or lazy update or this kind of technique, the idea is that we want to update ranges of positions. So we can query range of position, but we also want to update a whole range. Okay, so for instance, a typical application is, okay, we are querying minimums and we want an operation that says, okay, from this position to this position, add some constant, like add 5 to all positions in this range. Okay? This is the simplest example. So the idea, so of course, if we do that one element at a time, it's going to be really slow because the ranges can be linear. So what we're going to do is, instead of updating values, we're going to update any. We're going to let ourselves to update any node in the tree, be the divs or any internal node. Okay. So we're going to say something like update 1 to 6, and then we're going to do the same procedure we do for queries. we're going to take the 1.6 and then maybe split it, and we are only going to process the update. Okay, so for queries we remember, okay, we need a minimum of this. Then we partition this into this, and then we ask for the minimum of 1.4 and the minimum of 4.6. Okay, and we proceed recursively. So for updating, we are going to do more or less the same thing. We are going to say, okay, update, so update with this operation, the range 1 to 6, and then we are going to split it and going to say, okay, then that means updating 1 to 4 or 4 to 6. Okay, and when we get, the only difference is when we get to a node that is exactly the range we are trying to update. Okay, so for instance, suppose we, in this case, then 1.4 is going to get split to 1.2 and 2.4, and then 2.4 is exactly this node. So then the idea is that we stop and do not propagate the update. I mean, if we propagate the update up to the leaf, then we are going to get linear time outputs. Okay? We need, as we do in the queries, we need to stop here. So what we do is we store this data. Originally only talks about how to solve the queries for asking for minimum or whatever. Now we're going to have also in this data that we keep in the nodes, we're going to also know what is the update that is pending for this range. Okay? So, I know this data says some minimum, says something like min equal to 17. But now, for one particular node, and now it's going to say something like update equal to plus 5. So actually probably just 5 because it's going to be some integer variable, but some data that represents the updates we want to do. Okay, so if an internal node has this, that means I should be. So I am thinking that all the nodes behind this, so all the leaves that are covered by this range, should have plus 5. So should be 5 more than they already are. Okay, so we don't update the array directly. Okay, and the invariant that we maintain is that we do not access any node that has pending updates over it. Okay, so as long as no one tries to split, no query, be it an update query or a request query, tries to split here, then we keep the plus 5 here. Okay, we never propagate it to the leaves. If at some point some query arrives here that requires us to split into its childs, then we propagate the update to the child. And in this case, propagating the update is simple. It's just, okay, then I tell my left child and my right child to add 5 to their corresponding leaves or whatever. Okay? If we get to the leaves, then of course you never split in the leaves, so the update can remain in the leaf forever. Okay, you can actually do it in the data if you want. Okay. So for this to work, we need a couple of things about how the updates and the queries work between each other. Okay, because since we are not going to be updating all the nodes, then that means that we need to be able to recalculate the minimum based on this update. Okay, but with addition and minimum this works out well because, okay, suppose we have a node that represents some range. It really doesn't matter, the idea is that it doesn't matter which range. It doesn't even matter if this is a leaf or an internal node, because leaves are just ranges of size 1. Okay, and you can treat them identically as you treat the internal nodes. Because the ranges of size 1, the only good property about them is that you're never going to split a query in half because there's only one position. Okay, but other than that, you can use exactly the same code to update leaves that you use to update internal nodes. So, when you update something in this node, you say, okay, I'm going to be adding 5 to all the range represented by node. Okay, so that means the minimum is good. So of course the minimum, the new minimum is the current minimum plus 5. Okay? So we're going to have something like, okay, this has min equals 17 and update equals plus 5. And this is going to have maybe minimum equal 13, and this has minimum equal 17. one of them has to be 17, and this has no update. Okay? So when we get this plus 5, we are going to add 5 to the minimum. Okay, so now this minimum is the correct minimum, but these two, the child and everything that's below this is now outdated. Okay, it has incorrect data. Okay, that's why we cannot access this node because we are going to get incorrect data back. Okay, but the good thing is that since we are doing everything top down, then the only way to access a node is through its parent. So the parent knows that it has pending update. Okay, so whenever the parent needs to access the child, he's going to say, okay, you two update yourselves also, and then it's going to access you. Okay, so when the query comes, so when the query of the, well, when a query comes that requires splitting, then before splitting you say, okay, you left child update yourself with plus 5, right child update yourself with plus 5 with this range. Okay? Sorry, not with the entire range, because if we are using the entire range of this node, of course it covers the entire range of all the childs. Okay? So update yourselves, and then it splits the query. And continues. So what happens is that when the parent tells the child to update themselves, then the child do the same. They keep the updates for themselves. So this says plus 5 and puts an 18 here, and this puts plus 5 and puts it 22 here. Okay? And they also don't tell their own child, right? Because there's no need to. This is the lazy part. We only propagate the updates whenever it's required. Okay? So now since we have the query that's split here, then these two are going to get a request. And then if the request that they are getting requires more splitting, then they are going to propagate the update to their own childs and so on and so forth. But in general, we only propagate updates as a result of some query wanting to split in the node. Okay? Okay, so but it's important that we know, in this case, for instance, how to calculate the minimum for an updated operation. Okay, because we need to keep our data to return queries up to date. Okay, we cannot recalculate recursively because our childs do not have good data when we are updating. If we need the child to have good data, then we cannot do this stop propagating, and then there's no point of the delay update. We cannot delay anything. Okay? Okay, and then the second important invariant that we need is we need to be able to combine several updates. So in general, it's more or less like the update operation has to be associative in some way, at least to the left. Okay, so for instance, suppose maybe a later update says to this node, okay, now we have to add 6. Right? Let's go back to the state in which you know nothing about the update yet. Okay, so if a plus 6 comes, that doesn't require to split. Okay, I should be keeping the update in this node. So in this case, it's easy because since it's addition, then okay, I have a plus 5 pending and a plus 6 comes, then I have now plus 11 pending, and I update again the minimum to 28. Okay, so then we can accumulate several updates into just one update. Okay, so these are the two things that we need to be able to use lazy propagation or delay update or whatever in segment trees. We need to be able to accumulate updates into just one update, and we need to be able to perform the update in the accumulated data to return queries. So minimum or maximum or whatever we're using here. Okay? If one of these things fails, that means we cannot use it. Okay, sometimes we may need to generalize the concept of update from the one that comes in the problem for this to be true. Like, I don't know, if the updates are, and suppose the problem says something like you can update by adding or multiplying. So the update is add to this range or multiply this range by some constant. Always possible. Okay? And then it wants to request minimum of some range. Okay?
then I cannot accumulate both addition and multiplication and just addition and multiplication. I need to combine. So that if I consider like applying a linear function to a range as an update, that generalizes both addition and multiplication, and then I can combine because applying a linear function to a linear function is a linear function. So, have you understand this? So in each node I will keep, okay, multiply by this and add this. So if when you multiply, so suppose we have, so now we have add 3 and multiply, this is what we have multiply by 2. Okay? So it's first, actually this is first multiply by 2 and then add 3. Okay? And then if more additions come, then we just increase the addition. But when multiplication comes, we know that we have to multiply by 2, then add 3, then multiply by something else. But that just means, okay, so suppose then we get, you know, times 5, then the overall result is just multiply by 10, because times 2 times 5, and the addition is also going to get multiplied. Right? Because the idea that we are doing this is multiply by 2, add 3, and then multiply by 5. So this is the same as multiply by 10 and then add. Okay? Because of commutative. Okay, so with this kind of technique we can both add and multiply a given range. And this works because of the commutative property between addition and multiplication. Okay? But at least in this way with generalizing, we need to be able to accumulate several updates into one node. Because this is going to happen, especially in the nodes that are close to the root. Okay? Okay, so this is basic propagation. So now the good property of this, so it has a lot of requirements, but the good property is that we can both query for something in logarithmic time and also update something in logarithmic time, or okay? Because since the updates only propagate themselves when a split on query is already happening, then of course they are not going to add any extra cost to the cost of the general. Okay? And well, I think with this top-down implementation, it's easy to manage these updates. Okay. So the second question is, how do we apply this to the problem? Okay, so do you want to tell this part? One view of this?
Come there and explain. Okay, so basically you have like this small string and the big string, and the sec tree will give the nodes will be all the substrings of the length of this, which are this one. So I have a node here with this string, a node here with this string, another here with this string, and so on. For each node, initially I will calculate this match, and I create a sec tree with those values. And for each node, I will give like if it contains a string equals to this, and if it does, I will give like the biggest and the smallest mismatch inside those. Because when I give an update with the interval, the new biggest value will be like the size of this minus the size of the smallest mismatch. So with this I can update intervals and make the curious. And there's like a corner case that if you update one interval and there is a matching of this string like help, F, inside help, outside, you have to update it manually, one by one. But this is like smaller than 5, so you can go one by one here.
Okay, so and how I'm going to recapitulate this. So how do you do to update manually, because you don't have the, so you don't know exactly the case of all the.
I kept a binary index tree.
Oh yeah, a separate tree just for the binary part.
Going like for all the letters, how many times I swap those, and then I can do this magic.
So I will basically say the same, but maybe a bit more detail. So the idea, so you say it's exactly as he explained. So we have the big string, and we have the uppercase and lowercase, and then we have the small string. So first we calculate the matches, the case-insensitive matches of the small string inside the big one, with just brute force, because since the small string is really small, this is not going to take a long time. And wherever there's a match, then we say, okay, here we have a match with this kind of, with this vector, with the name, case something. With the mismatch. So we keep the mismatch at each position, we keep the mismatch between the substring that begins at that position and the current T that we are supposed to search. Okay? This we do a pre-processing at the beginning. So now our operation, so our query operation is going to be just the maximum of these values. Okay? This is the query operation we use in the second. And the update operation is flip the case of this range. Okay, when we flip the case of a big range, okay, all the instances of T inside are basically, the case on them is completely flipped. Okay, so if the mismatch was K, then the new mismatch is the length of T minus K. Okay, because the ones that were matching now don't match, and vice versa. Okay? This is true for all the instances of T that are completely inside the interval we are flipping. Okay? So the idea he was saying was that we can store in the segment tree both maximum and minimum of the range. We are only going to be querying maximum, but we keep the minimum to be able to update this. Because so when we flip, the minimum, the new maximum is the size of T minus the minimum, and the new minimum is the size of T minus the maximum. Okay? Because the maximum is going to be the size of T minus something. And for it to be maximum, we have to subtract as small amount as possible. Okay? Oh, and this is dual reason. Okay? So in this way, whenever we can update, we can not only update, with basic propagation, update range, but we can also maintain our invariant about the value. So in this case, you have to generalize which data you need, which recursive data you need for the queries. And we have to also maintain the minimum that we don't need to return queries, but we do need to update whenever there's a flip. Okay? And then the corner case he was talking about was that we may have some instances of T that lie a little bit inside the interval and a little bit outside the interval. It's being flipped. Okay, and for those we don't really know what happens. So those we have to examine manually. But examine manually is not so easy. Okay? That's what made the problem so long. Because since we are doing lazy propagation, we don't, the structure, we don't really have updated data on the case of all the letters here. Okay? Because there may be several flips that happen that have not been propagated to these leaves. Do you understand this? It's like in the previous example, if I'm doing lazy propagation, I cannot go to the array and find out what this value is, because this value may be missing some updates. Okay? Because because that means basically accessing a node forbiddenly. So accessing a node, we said we will not access a node if it has some updates on top. And for us to be sure of that, we should not access any node without going through its parents. Because going through its parents is the way to ensure that when we access it, it will have all the updates made. Okay? So we can do several things. So one thing is forget about the data, so don't use the array, and keep some sort of additional structure that knows what the case, that knows or allows us to calculate what the case. We know there's a match, right? Because matches don't change by flipping the case. But so allows us to recover which case each letter has. So this is more or less also the first idea I did, was to have a separate, because we can store in a separate tree. Okay, then you have a flip from position I to position J, right? And we have several of these. Okay, so basically what we need to know to decide the case of a particular position is just how many. So this is basically a +1 in I and a -1 in J, and everything is modulo 2 or something like that. So we have to know if the number of updates made before the position it's odd or even. Okay, counting both. Okay, so if you are after J, then you are adding an even number of updates, so no change. And if you are below I, you are also adding an even number of updates because there's nothing. But if you are in between I and J, you are going to be adding 1 to the total number of positions below you that were updated. Okay, so that means that you are changing the case. So we, in a single set, this can be like set from the STL. We only need to be able to calculate how many less than, or multi-set maybe, how many less than this position there are. There are several abstractions for this. It can be binary extensive tree. You can also use some. What I used was a second copy of this of the segment tree because I already had the segment tree coded for the other part. But you only need this kind of query, okay, to decide the case. And then you get log for each, but this is really small because this is only 5, so there's only at most 25, and practice much less instances of t, and then each of them we calculate manually, and after we calculate manually, we have to update the structure. Okay, we say, okay, the new value of this, but then updating, we can do a regular update here. We just update the value and then go up, updating everything, like we used to. Okay, because we know how to combine updates. So. But the easiest way to do this is, okay, if we want some data, let's access the node that has the data. Okay? Oh, sorry, of course, besides maximum and minimum, we can remember, but if you do this, it's not necessary, but we can remember as a Boolean whether a given range is flipped or not. Okay, at the beginning everything starts at false, and then when we have this true, that means okay, I should flip this, but my child still don't know how. Okay, and this is easy to combine because if we have two flips, they cancel each other out. So we turn the Boolean back to false, and if we need to split, and the Boolean variable is true, then we tell both our childs to update themselves with a flip, and then when we do that, we put the Boolean back to false because in this node there's no pending update. Okay, like here, when you have the update of 11, if you split and send the 11 to the child, then this gets to 0 because the pending this only records pending updates. Okay, and each pending update should be only one node for each branch in the tree. Okay, so when I split to my child, I have to forget about the update and everything is cool. Okay. So what we can do here is some sort of special treatment in which we have two kinds of data. We have the data about maximum, minimum, and that sort of thing, and also the case for each position in the original string. Okay, and then if we want the case of a particular position, we access it through the tree. Okay, and accessing it through the tree means whenever we are branching, we are propagating the updates. So whenever we get to the particular position, the case was already updated for all the flips that may have pending. Okay? So when we get there, we can know the case, whether it's uppercase or lowercase, which is basically the same as doing a separate tree, but only that we're using the same tree. Right? We are using the same tree both for the max min things and to know the case of a letter. Another way to know the case of a letter is, instead of, do not change the tree, just go, so if we want to know one position, go through the tree and count how many flips the position has spent. Okay? Because we only need to check the path to the root. If it's odd, then change it from the original. If it's even, maintain the original. But still, we are taking logarithmic time to know the case of each one of these letters, but there are not so many of them. We only need to ask for the case for at most 10 letters. Okay? Because all these overlapping only use letters up to 5 from the end on the first one. Actually, this is 4. Okay, so just take letters on each side. Okay. So if you didn't, I recommend that you implement this because there's plenty of details to manage and well, you can practice the structure. If you are really brave, you can do it with dry instead of regular segment tree with arrays. Like the technique I explained yesterday to do segment trees. That is going to be annoying at first, but then I think when you get used to it, it's going to be much easier than regular segment trees. Because you're going to be using the same structure for basically everything. Sorry?
With no map?
Yes, well, in this case, since it's binary, you can use 2 pointers. Yeah, you can use map from int or from char to...
It's not very slow.
No, because the map has 2 elements. I mean, yeah, it's a little bit slower, or maybe much slower than an array, than putting the 3 on an array, because in an array everything works really fast, but not a lot slower. I think they should... I don't think some problem is going to work by using arrays, but not using the other. And the idea is that recursive implementation, I mean, since the algorithms are recursive, having also a recursive data structure makes everything easy. You have the recursive algorithm, but on a non-recursive structure, then you have all this additional work to work out, okay, the childs of node I, there are 2 I. I know it's not so difficult to calculate, but it makes you have some math inside the algorithms, and then can you have like 2 algorithms working in tandem. So it makes it harder to read, harder to spot bugs. It's better to separate the logic of the tree and the logic of the actual structure you are putting on. Okay? Any questions? Okay. Okay, so let's try to do the geometry problems. The hard one first. So the last problem is the set. The mission impossible. Oh no, the second to last, sorry. Did someone solve this? There's no shame in not solving it. It's really difficult and long. Does anyone know how to solve it? Or has an idea on how to solve it, even if it has, I know, kilometers of code that you never wrote? Sorry? No? Okay. So there's at least 2 ways that I know to solve this. I'm going to explain the easy one, that is not really easy, but it's easier. So one is doing a lot of work with, and then doing some things with dual graph. You were talking about dual graph with Jacob last week, right? Okay, so this is more or less something that looks like a planar graph. It's not really a planar graph, but you can manage to make it a planar graph, and then take the dual graph, and then take the and then calculate what informans this is are in the same area as you are. So let's think about the segment for it. So we have a polygon that represents our country, simple polygon, and then we have some circles that represent radars that are basically forbidden areas, and here, and then we have some points that represent people. One point that represents you, that one of you. And then all the other points represent people that you want to talk to, right? And basically the question of the problem is, tell me one of these that I can talk to, or if there are several, take me to the one that has the highest priority, where the priority means the distance from the point to the polygon. Okay? But since there are only like 1,000 points and the polygon is 1,000, just by brute force we can calculate the distance from the points to the polygon, because it's just trying each border and calculating the distance from the point to the segment, which is constant time. So that part is not so big. Okay? Let me skip that the part of calculating, and let's assume that we have the priority for each of the points, and then it's just, okay, for each point, is it reachable from me or from you or not? So these two are not, because we will have to go either outside the polygon or through these radars, and these four are reachable. Okay? And then from the reachable set, we take the one with maximum priority or with lowest index if there's a tie, and that's it. But the only important part is really given 2 points, knowing whether you can reach one from the other or not. So the difficult idea that I'm not going to work out is we can make a graph here where each circle is a node and each side of the polygon is a node, and two things are connected if they overlap. Okay? The problem is that this graph is not planar because, well, you can have something like this. And basically this is a K5, or so a complete graph of size 5, and this is not planar. Okay, so we need to do some work to start removing circles that are not necessary, that are completely covered by other circles, and after we remove circles that are completely covered by other circles, then the graph is planar, and when the graph is planar, we can take a dual, and then we can calculate the region where each of these are. But this it's just 1 minute for me to say, but calculating the region where each of these are, it's really complicated, because you need to go around and check all the borders. It's really something. So I'm going to explain an idea that is also complicated, but I think it's more manageable. At least more modular. So reachable. So let's concentrate on 2 points. So reachable means that I can go walking from one point to the other. Okay. And so of course, if there's a line of sight that is not cut by any side or any circle, then it's reachable. But of course, we can have something like in here. So let's start with no radars. So suppose, because I don't really care about the polygon, but if it's a polygon, see there's a single polygon and no radars, of course it's going to be reachable because the polygon is simple. But let's suppose instead of polygon we have like several walls. Like, because for this purpose it's the same. Since the walls are touching each other, they are not going to let me go up. So we have 2 kinds of walls. We have the like segment walls and we have simple walls. Okay? So suppose you have 2 points.
You can pass through the point. You can pass through the circle, but the point of the polygon you can pass.
Oh, this is easier than I thought. You can? Sure? Yeah. Okay. Well, that's easier. But, okay. So let's think about this problem that maybe you already know, or
So suppose you have 2 points and you have lots of walls. You want to know if you can reach one from the other. So what do you do? Because then with circles it's just a matter of a little bit more geometry, but more or less the same idea. So if you have a lot of wall segments, so that means intersect, and you want to go from one point to the other, you know how to solve this? Okay. So the idea is basically going from one point to the other is seeing if there's a path, and the path, we can assume the path to have the following way. We get from our point to some border, then we go along borders, then we walk through walls, go through touching walls, and then from the other wall we go to the first one. Okay? This case, no. Well, then we have to, in this case, we have to consider 2 cases. One case is when both points are in the, let's call it, outside area. Okay, so let's say they can reach the point plus infinity. Okay? Or it's possible that the 2 points are surrounded by walls, but they are in the same area. Okay? For the first case, so what we do here is partition, in that case the segments, and in this case the circles, we partition them into segments. Okay, so we calculate the intersection between circles, or between segments there, with brute force, because there are not so many of them. And we partition. So we partition this circle into this segment, and this segment, and this circle into this segment, okay? So segments without any intersection. So I know for this circle right here, we are going to end up with this, and this, 4 segments. Okay? And yeah, for this it's also 4, and so on. Okay? And it's and then for each circle we can calculate which of these segments are actually outside any other circle. So let's say there are borders. So consider the union of all the circles, and we want to know what the border of this is. Okay? To calculate the border of the union of all circles, we can just go circle by circle and say, okay, from this particular one, which parts of it are actually outside or in the border of the union of all circles. Okay, so we consider one circle and we consider the others. We say, okay, which parts these other green circles are covering. Okay? This is just a matter of calculating the intersections and then doing some interval intersection trick. Okay, I already explained this a couple of times. Okay, but we can calculate these intervals as angles, for instance, angles from the center of the circle, and then do interval intersection to calculate the union, and then take the complement, and then we will find out that okay, we have this and this and this and this and these intervals that are actually borders. Okay. And not only that, but each of these intervals is going to be, we know which circle it's touching. Okay, because it's the intersection that made this segment appear. So this intersection and this intersection. Are you following? Let me know if you're lost. Okay. So for one circle we iterate the others, we calculate for each which is the covering segment. Then we take the union of the covering segments, and then we take the complement, and that's the uncovered part of the border. And then for each uncovered part of the border, we calculate which is the adjacent circle. So then we end up with a lot of these segments. Right? We have some segment here, and then some other segment here, some other segment here. And we have this kind of wall, right? Made of little parts of little segments. Okay? So, how do we know? So we have these kind of walls and we have the 2 points. So how do we know if we can reach one from there? So the idea is, okay, let's walk from the point to any of the walls that I can reach without crossing other wall. Then go walk through the walls to some wall that we can walk to this point. Okay? Because
right? Where they cannot see each other, but you can reach one from the other. If you can reach one from the other, then you can reach it by just walking straight to a wall in a particular direction, like I don't know, left, like in the -1, 0 direction. So this one was here. And then we want to know if this wall is adjacent to this wall. If they are, that means that I can walk right next to the wall all the way up to here. Okay? And actually, so this works also in the outside, because in the outside, both are outside, then we're going to walk, one there, we're going to walk to the wall, turn around, okay? So a couple of things, guys. First, of course, we are going to remove every informant that is already inside the radar. Those we just delete because we know they are not, we cannot reach them. Okay? After doing that, we can remove circles that do not intersect any other circle, because those are not going to block us from passing. Right? If you cover, like here, one isolated circle, it's impossible for the circle to actually isolate us from any other one. Right? In order to surround something, you need several. Okay, so if they are isolated, because this is not really a segment, and consider this a wall is a no. It can be done, but it's better if everything is just segments. So at least one intersection. So let's just remove the circles that have no intersection with any other circle. Okay? If you want to do it, you can also remove circles that are completely inside another circle or something like that. But that's not really necessary. But it's important that when you calculate this, if the circle is completely contained in another circle, then you need to detect that separate, right? Because then you are going to get no intersection. So when you iterate the circles to calculate intersection, if one circle completely contains, then this circle has no action. Then we have to detect that this circle has no segments to contribute to the border. Okay? So these are two cases. Either it's completely contained or it's intersected. Of course, being intersected, it can also happen that it contributes nothing. Right? Like this. It's not containing any of the other two, but it's not contributing any border. But then, when we take the union of all the intervals, of all the covered intervals, we're going to find out that the union is actually the whole circle. And then we say, okay, no border, let's move on to the next step. So we build all the segments. And then for each, so we need, after we build the segments, we need to do two things. First, knowing for each segment which other segments are adjacent. But that can be done directly when we calculate the segments. We remember the circle and the point at which a given segment was built. So when we build these segments, we have to remember this intersection and this intersection. Okay? And then we can match this intersection with the same intersection when we process this circle. We're going to consider this as an intersecting circle. Okay? This is one point. And then we're going to process this intersection, and we can remember, because it has exactly the same position and everything, that this is the same as this one. So that means that this particular part of the border that we know is going to be uncovered, right? Because it's not going to be another one here. It's adjacent to this part. Okay? Okay, then we know we have some borders and we have adjacencies from the borders, and then all we need to know is, for each point, be able to calculate one border adjacent that it can be reached from the point. So what we can do there is, if the point is too far, so if the x-coordinate of the point is farther to the left than any border, and the y-coordinate is farther to the farther up than any of the border, then the point is outside, right? And the same if it's so we consider all the borders, and since we have everything with coordinates, we say, okay, let's calculate by taking mean and max of the x and y coordinates the bounding box of all the borders. Anything that's outside the bounding box is outside. Okay? And if it's not outside, then we can just, for each point, consider the line that goes straight down or straight to the right or straight down or straight to the left, and then check the distance between. Oh, that works without those. Okay, so let's just calculate the distance for each point from each point to each segment. Then the segment that is closest, then that is reachable. Okay. So let me rephrase it. Let's forget about the box because I didn't notice yesterday that this was not necessary. Oh, because I thought we had the polygon.
Oh,
Yes.
I got accepted with this problem yesterday at night, but I don't know if the solution is good and it extends to the other.
Let me just finish wrapping up and then we. Okay. So then, whichever of the segments is closest, then we know it's reachable, right? Because in order to block the path from the point to a wall segment, there has to be another wall before, so it's going to be closest. Okay. So the closest one is always reachable. So, and we don't need any of the reachable ones. So we get the reachable one from each point, and we have to take some care so on which side it's reaching. So if it's reaching on the inside or on the outside, but that's just some trickery about checking the coordinate from comparison. And then we check whether the two borders that are reachable between from the 2 points are actually the same connected component of borders and on the same side. Okay? Then, if you want to go ahead and implement this, it's going to be a long time, but it's also a practice for geometry. So, okay, so what? Yeah. So let's see another solution. Well, I guess another different.
To this problem, the solution I found is that when you have a circle, it blocks you on only 2 ways. The first way is when the informer is inside the circle and you are outside the circle. Then you can't reach the informer, and you can check all the circles and see if the informer is any one of them, and if it is, you can reach him. The other way is when the informer is here and you have a lot of circles and all of them make a wall and the informer is inside. And if you take the 2 centers and makes a line, this region can be seen as a polygon, and the informer is inside the polygon. So if I can get all the polygons and check if the informer is inside any of the polygons, I can reach him. And if I take the center of the circles and make them nodes and perform a DFS to find circles, these 2 circles have intercept each other. Then I make an edge. So if I make a graph and find all circles on that graph, I can take these circles, get the polygons, and check if the informer is inside that polygons.
Right, that they can be an exponential number of cycles.
Yes, but I will not do this for every circle. If I had something like that, I can have a lot of circles, but on a unique DFS, I will not find everyone. I will find only some of them.
Okay, so how are you sure that the cycles that may block you are found?
because I will find that circle, and I'll find that circle too, but they cover all the path, all the regions. This, if the informer is inside the circle, is inside one of them.
Yeah. I'll have to think about that. Okay.
And I don't know if that problem I can do the same. Maybe I can two segments that intersect. I will make an edge and do a depth pass, and then check all the circles, all the polygons.
Yes, it's just so this idea in the segment case, this is the dual graph idea. Okay, basically, so some modification, but this is basically taking the graph of the circles, how they intersect each other, and then take the dual, which is the regions. It's just skipping some parts that are annoying, and that's good. So in the segment case, you can do the same, but it's more annoying to check which region a given point belongs to. So in this case, you say, okay, I just build this polygon and check in which polygon is the informant or the spy. But in the other case, it's not really a polygon, right? Because you can put the point anywhere in the segment. So here, so you say, okay, let's consider, for instance, this region like this. If we consider the cycle in the graph, we can make a polygon like this, but the polygon is going to do something like this. So if we make a polygon like you made for the circle, then if the person is here, you're not properly detecting where it is. So you need to detect actually this polygon. It's important. In the case of the circle, it doesn't matter because it's a little bit big. Then any polygon that goes inside the circle is going to work. So this is smart. So, and this detecting this polygon is basically doing that I explained for segments. For segments it's easier because intersecting segments and taking parts and taking distances between segments is easier. Now it's circles. Or with pieces of circles. But it's just the difference between this and that is just how much math you need to take the distance and intersections. Not really a different factor. Okay. Okay. So let's. I want to do one more before taking a break. So let's, because the other two geometry problems are really related, so I want to do them both more or less together, at least not with the break in the middle. So let's just go to electric needs, which is some more in the middle. So I'm sure some people here know how to solve this because I already explained it in some previous training camp. But there's not a lot of intersection, less than so anyone solved it? No, right? Yesterday? Did anyone know how to solve it? Or has an idea? Yes. So what's your idea?
Use binary search plus union of this plus.
Right. So that's pretty simple. So how come nobody solved it? So this is again what I will be talking, right? Sometimes you have a simple idea and the idea is correct, but then you don't get to solve the problem. This is a good point to concentrate and try to improve for complex results. I know it's much more fun to learn about algorithms or new data structures or new techniques, but this really is going to impact heavily on your ability to get more accepted problems during complex. Okay, it's important that when you get an idea, it's not easy to get the idea to solve a problem in the workflow. So that's hard enough for you to be in a situation in which you have the idea but you don't solve the problem, right? Like in this case.
I know it's long and everything, and I know it's not trivial to get from the idea to the solution. There's lots of details to work out. But once you start to get used to solving this kind of problem with this kind of long jump from the idea to the solution, then it's not going to feel so much trouble when you do it, even in a completely different setting with different idea. You do it for one geometry problem and one binary search problem, and I don't know. But then when it's the same kind of long jump in an arithmetic problem, it's still going to be useful to you to have this practice of, okay, let's work out all the details and do everything, even if it's long. Okay. So in the problem, it says we have a rectangular grid of cells with lots of cells, and then we have some power plants inside the grid. And we are basically numbering the cells here according to first how close to a power plant they are, and second how high they are in the number of row, and third how to the left they are in the column. Okay, so in this case we will be numbering something like 1, 2, 3, 4, 5, 6, 7, 8. No. 11, 12, 13, and then this has priority 2, all this has priority 2, this has priority 3. No, okay. So then we will have 14, 15, 17, 18, 20, 21. No, 1. Okay? But you have a more or less better drawing in the section. Okay, so as he said, the idea is to do binary search. Because what we are going to do is first find the electric priority. So the distance to the closest power plant is called the electric priority of a cell. Okay? And the numbering is first decided by electric priority, then by row, then by column. So first lowest electric priority, then lowest row, then lowest column. Okay, so and we are saying we're given a number and we're asked which cell has this number in this list. And since there are a lot of them, we cannot really actually simulate this process. So what we do is first to find which is the electric priority of a cell that has, so we're given a number I, and we're asking what's the ith cell in this list. So what the first thing we want to find is what's the electric priority of the ith cell. Okay? Which is to say, so we can have, I know, let's say 13 cells, priority 1. No, 12 priority 2, 5 priority 3, and so on. Something. Okay? Okay, so if I is between 1 and 13, then the electric priority of the ith cell is going to be 1. If it's between 14 and 25, it's going to be 2, and so on and so forth. Okay? So, if we had this list, we are not going to build this list physically, let's say, in an array or anything. But if we had the list, what we would do is accumulate the numbers, right? Say, okay, I will write 13, and then 13 plus 12, which is 25, and then 25 plus 9, which is 30, and have the accumulated, so then we know the range for each of the cells. And if we want to find the particular I, we can just binary search this accumulated array and find out where I lies, right? We want to know the first item, the first number on this list, on this increasing list, now this accumulated, the first number that is not less than a, not less than I. Okay? And that's going to represent the electric priority. So if I is between 26 and 30, we're going to find this, because 30 is not less than I, but and it's the first. And if it's between 31 and 40, we're going to find this, and so on. So binary searching for the first not less than I would give us the electric priority in logarithmic time. So what we are going to do is basically having this list, but symbolically. Instead of actually building a list with all numbers, what we want is a query, be able to query what each of the numbers is. So this number is the number of cells with priority less or equal to 1, then this is the same, less or equal to 2, less or equal to 3. Okay? So what we need is to be able to find out number of cells with electrical priority less or equal than k for a given k. Okay? And with that query, if we do that query in an efficient way, with binary search, we can find what's the electric priority of the ith cell for any I. Okay? Is this part clear? Good. Okay, so how do we solve that query? So since we only need to separate between less than k and greater than, well, less or equal than k and greater than k. And that is much easier than separating all the possible electric priorities, because each power plant has a fixed range of cells for which a particular power plant makes them have electric priority less than k, or less than or equal to k. Okay, let's suppose we have a big grid, and we have a power plant here. And then if we have a square, we build a square of size, we say this 2k plus 1. Right? Yeah, 2k plus 1. 2k plus 1. So k for each side. Then this is the square of all the positions that have electric priority less than or equal to k, thanks to this power plant. Okay? Of course, some of them may have, but we know all of these have to be counted for as cells that have electric priority less than or equal to k. And we know that all the other cells, if they are counted for something that is not this power plant. Okay? So basically, when we have several power plants, we are going to have several squares, all of the same size, not as in my drawing, on the grid. So what we need is the size of the intersection of all these squares. This is exactly what we are asked, right? All the sets that are close enough to some power plant. And then, since there are only a small number of power plants to intersect, we can do some coordinate compression, and then say, okay, let's extend all these sides and these. So we partition the grid in all the x coordinates in which a border of a square is, and all the y coordinates in which a border of these squares is, at this one. Okay? And then we know that in each of these sectors, either there is square or it's not. Okay? Because we are partitioning on the borders. Inside the sector, it cannot change from a cell being close to a power plant to a cell being far from a power plant. Where close and far are defined as less than or equal to k distance or more than k. Okay? So then for each sector we shall test one cell to see if it's close or far from power plants. We can just do that with brute force checking for each power plant the distance. And then if it's close, then we add the size of the sector. And if it's far, we don't add it. Okay? Then we can solve this query. And this will be time for each query. We are going to take time number of power plants squared, cube. We can do it better, but it's not necessary because this has p squared sectors. Because we have p vertical, 2p vertical lines and 2p horizontal lines. And then for each sector, we have to iterate the power plants to see how far they are. So you can also do this in p squared or even better, but it's it's not necessary for this log because P is like 20. And then we have the log. And then for the binary search, since the electric priority can go up to n, the size of the yes, n or m, log of m1. Okay, log of the size because it's the maximum electric priority. Okay, for the binary search. So this time it takes us to find out what's the electric priority of the ith cell. Okay? So now that we have the electric priority, we can do a similar trick as this, but a little bit more careful. We have a power plant. I want to know, okay, which things may have, so for something to have, so let's say we found exactly the priority equation. Find out that electric priority of the ith cell is A, some internal. Okay? So for that to be true, the cell has to be at distance exactly E from some power plant. Okay? So we can discard most of the grid. So for each point, we do the same. We take a square of size 2e plus 1, and then we take another square of size 2e minus 1. And then all of these cells in the border, let's say, the square, are the cells that are at distance exactly E from the power plant. So these are candidates at least to be the ith cell. Right? And we have, of course, 20 of these kind of things. Okay? Good. So, and of course the problem is that some of these may not be exactly E. It's possible that some of these of the power plant close, so these are not, they don't have priority E, they have less than. Okay? So let's consider this set of candidates as the union of these kind of squares. Okay? We also know, since the last query of this binary search is, or we can do an extra query to see, okay, how many cells have priority less than E, or less than or equal to E minus 1? Okay? So these are all the ones that are before. So let's say we have J cells with priority less than E. Right? Then this means that the ith cell is the I minus j among priority E. Okay? So we subtract to the index we are looking for all the ones that have, all the cells that have less than. So if we number only the priority E, then this will be the number of the cell we are looking for. Right? It's just shifting all the numbers. Okay, is this fine? Okay. So now what we do is this thing here, we do the same trick with the sectors. Right? We take all these horizontal lines and extend, and all the vertical lines and extend. And then we have several kinds of sectors. We have some sector may not be a candidate because it's not at distance E from a power plant. So we iterate the sectors in first rows and then columns order. Okay? If a sector is not at distance E from a power plant, then we discard it because we are not even considering it. If a sector is at distance E from a power plant but is at distance less than E from another power plant, we also discard it because it's not a sector of electric priority E. So the invariant of this sector is that either all the cells in the sector are priority E or no cell in the sector is priority E. Okay? A sector may have mixed priorities. It may have several priorities other than E. right? Because these lines are all the lines that separate. So all the lines that separate priority E with priority non-E, or that potentially separate a cell with priority E from a cell with priority not E. Okay? So each sector either has all its cells with priority E or no cell with priority E. So testing just, I don't know, the upper left cell of each sector. Again, by testing we mean iterating through the power plant and calculating the distance. We know whether each sector has all its cells E or not E. And so each time we find the sector that has all its cells with priority E, what we do is we check, okay, the size of the sector is greater than I minus j. If it's greater, then that means what we are looking for is inside the sector. Right? We have a current index. We have, okay, now we are looking for the kth cell in whatever is left to check. We arrive to the first sector that is candidate, that is effectively all things of electric priority E. Then we say, okay, if they are at least k, then that means the k of this is the result. Okay? And then we just take the k, which is just since all the sectors in priority E have k 1, the k is just moving from the upper left k to the right. Okay? Is this fine? Okay, so we have these sectors, right? The sectors of main. So the sectors that have priority E always have height 1, because they are made of parts of these squares who have height 1. Okay, so we may have two adjacent ones. We may have like, I don't know, some other square that have here and make these two rows have both priority E, but since there's a line here, they are both going to belong to different sectors. Okay, even though they are adjacent and priority E. So when we arrive to priority E, we iterate the sector. So we are looking for the k. First we find the sector, so let's say we're looking for the 16. We find the sector with size 5. Now we say, okay, the 16 is not going to be inside this sector because there's only 5 of them. So if it's 5, then from number 1 to number 5. Okay? So what we do is subtract the 5 from the 16. Because now we want the 11th of what's remaining. Right? The 16 overall is the 11th if we don't consider the first 5. Okay? It's the same we did when we removed the other priorities. So let's say that then we find the sector that has 10 or 9. Right? And we say, okay, 9 is still less than 11, so the 11th is not going to belong to this sector. Right? So now we need 11 minus 9 equals the second of what's remaining. Then so the next sector has 7. Okay. So now the second of this sector is the second of what remains, so it's the 11th of this part, so it's the 16th of all the electric priority E, so it's the correct answer. Okay? So we arrive to a sector that has more cells than our current index tells us to find. Then in this sector we find the correct answer, and the correct answer is this number, so in this case the second of the sector. So it's taking the upper left of the sector and adding this number to the x coordinate. Actually, adding this number and subtracting 1 because we are counting with base 1 index, not base 0. So if the upper left is xy, then the second is x plus 2 minus 1, 1. Okay? Because we just move in the x coordinate. Or, sorry, I lied. Why is no one stopping me from lying? So we have this height 1, but we also have these sectors that have width 1 and height more than 1. Okay? So, but with this kind of sector, we have to be more careful. Okay, so this is what we do for the horizontal sectors. So we have these. We can consider all the sectors here. We have several of these in a single row. Okay? So either if the sum of all the sectors in this big row is is either greater than the current index we are looking for or not. If it's greater, if it's less than the current index, then that means that the current index is not in this part, and we just subtract everything. Okay, so we add up all the sectors, all the vertical sectors, we add up how many cells they comprise. Okay, if that's less than the index we are looking for, then we do what we always do. We subtract this from the index and continue with the next row. When I mean row, I don't mean row in the original matrix, but row in this sector kind of thing. So big row. Okay? If the sum of all the sectors, I mean all the current candidates here that are actually at distance E is greater than the current index, that means that the current index is found in this part. Okay? But this part is so all the cells here is made up as all vertical sectors of this chain. Right? So let's say, I know, we have height equal to 5, and we have 4 candidate sectors. So 20 cells. Okay? Yes? And let's say the index, we said that it has to be less than 20, so let's say we are finding the 17th of this. Okay? So this, if you could think about the union of all these sectors as like a submatrix of 5 rows and 4 columns. Right? If we just concentrate on these 5 rows of this big row of the sector matrix, and only of the candidate sectors that actually work, then this is a submatrix, not consecutive, but submatrix of size 5 times 4. So then the 17th is going, so the 17th is going to be the 17th. So the first sector, for instance, the first sector is going to have cell numbering only inside this part. It's going to have cell number 1, the next is going to be cell number 6, right? Because it's going to, so the next sector is going to have 2 and 7, the third sector is going to have 3, 8. Okay? So simply by and this is numbered like this, right? So if we divide by the height, then we find out in which row exactly we need to be. And then if we take if we divide by the number of candidate sectors, we find out which row we need to be. And then if we take the remainder of dividing this index by the height, actually we need to do -1 for the math to work out. But so in this case, 17 minus 1 divided by 4 gives us which row we are going to be in. This is 4. So that means we have 11 here and 16 here. So it says that the 17 is going to be the 4th row. Okay? Because each time we do this, we add 4 numbers. That's why we need to divide by 4 to see which bus we are going to get the number 1. And the number of sector is just the same but taking more. So it's 17 minus 1 divided by 4. Sorry. So now we can subtract. So we can take whatever is left. So we can, okay, if it's the 4th row, then that means that there is 4 times 3, 4 times 3 full rows that we are removing. So this is 12. So now 17 is the 5th. Okay? That's just some math in the, it's just considering some math in the submatrix to find out the index, exact index in this one. Okay? So when you find the column, you don't find the actual, so the row is the actual row, if you do it without it. But the column is just the number of sectors. Then you have to do another pass through these sectors to find out the number of columns of the sector. Okay, so if you get, okay, this is the 3rd sector in this area, and then you go and find out which was the 3rd sector to get the actual column number. Okay? So as you can see, there's nothing really
hard about this problem. You only need to be really patient with the math and careful with the implementation and everything. So it's also a good problem to practice this kind of thing of how to jump from an idea which is simple enough, right? It's just a binary search, nothing really technical, to an actual working implementation. The good thing is that it's really easy to make examples for this problem, because you can draw them. Okay. Okay. So let's take a little break. Okay. So let's be back at 10 to 11. Okay.
Right?
Okay, let's continue. Hey, guys, relax. Okay, so probably less than an hour, so I'm going to try to explain the geometry problems, and then at least one of the string problems, and that's it for today. So we have two that use similar techniques. So let's start with hide and seek, that you probably know better because it was the last year regional. So in this problem has several points, several walls, segments, and everything is nice because there are no collinear points, which, as we are going to see, it's much better for implementing this. This is the kind of niceness I was talking about that we do in the regional that you may not find. Some kind of corner case that we remove on purpose.
that maybe in a world finals problem will happen. You have to deal with this kind of. Okay, so we have the points and we have the walls, and we are asked for some of these points, at most 10, how many other points it can see or it can be seen from, but okay? So for instance, from this point, you can see this one, you can see this one, you can see this one, but you cannot see the rest because they are covered by walls. Okay? Okay, so we are asked this for only 10 points. So basically, and we have like 10,000 points in this outer wall. Yeah, no, yes, 10,000 walls and 10,000 points. So basically, we may try to do something quadratic here, but it's going to be a bit slow because we also have to take 10 squares. Okay. Okay, but what we are going to do is try for each point that we need to find out. Do it for each point individually 10 times, or up to 10 times, depending on how many points we need to check. Okay. So I know some of you saw this, right? So we need to. So the first idea will be, okay, for each other point, let's see if this segment intersects with some wall, right? And this leads to very simple squares and square solution, or actually it's not n. It's we have k kids, k points, w walls, segments. I'm checking for each pair of kids whether there's a segment intersecting or not. It's k times n. Right? With a somewhat big constant because the segment intersection requires several operations. Sorry. For each pair of kids. If we do this for every pair of kids, if we do it for just one kid against all of the others, it's k times n. Okay, because we have k other kids, and for each of them we have to try all w walls to find out what's covering, and even if we randomize the order in which we check the walls, in the worst case there will be exactly one wall blocking the view for every kid, right? And this is the case pretty easy to build because it's just here. This is actually exactly more or less how some of the cases were built. Right, take 2 points and put a small wall in the middle that blocks. And then it's not likely that these walls are going to block the view for anything else. Oh, not just 2 points. Okay. So this is going to take 2. But it's the basic idea for the correct solution. So we're going to try to do this, but in a more efficient way. And believe it or not, this is more or less like segment intersection. This is an intersection, but we have lots of segments and we want to intersect. The problem is that we can have the opposite. We can have lots of intersections. Right? If we try to find all the intersections between segments, view segments and wall segments, we may have lots of intersections and we are not really interested in all of them. Right? For instance, if we have lots of intersections here, we really don't really care. We only care about one. As long as we have one wall intersecting with the view segment, we already know that the view is covered, and then we don't need to check all the other ones. Right? The problem is that the regular straight line approach for segment intersection, with a straight line that goes like this or like this, doesn't really process these intersections in a good order. Right? It's not easy for us to say, okay, you already processed this intersection that blocks the view, then okay, stop processing all the other intersections for this segment. That's not the simple task because of the way the algorithm works. So what we can do is process this in a better order. That takes advantage of the fact that we do not have any arbitrary collection of segments, but actually a collection of segments that are all centered around this one of the time. Okay? So what we do here is basically same intersection, but with a rotating sweep line around this one. Okay, and this sentence more or less summarizes the entire idea, and then we have a lot of tricky details to look at. So what's a rotating sweep line? So it's actually rotating sweep half line because so we consider some line that starts here, goes to infinity to one side, then we rotate this around the point. Okay? And as we rotate, we start to encounter the other point, and we start to encounter the walls. Okay? So what we do is whenever we encounter, so what we maintain is as we rotate. So rotating a line, of course, just means we have some floating point variable that represents an angle, but there are several ways of doing it. But the easiest way is just have a floating point variable that represents the angle of this line and make it advance from 0 to 360, or from 0 to 2 pi, depending on your choice of angle representation. Okay? And then this represented this moving, well, if we go from 0 to 360, maybe from this over to. Okay? So, what happens when we move this is basically that we encounter points, and the end point, we encounter points, and we encounter the walls in the sense that we encounter one or the other end point of a wall. Okay? So, what do we want? When we encounter a point, we would like to know, okay, can I see this point or not? Right? In order to decide that, we need to know, okay, which are the walls that are currently active. I would say a wall is active if the line is passing over it. Okay? Of course, when the line encounters, let's say, so when the line is over here, so when it's passing through this point, we have, of course, the walls that do not cross the line are not going to cover this point because the segment is a subset of the line. Right? So only walls that are over the line have a chance of actually covering the view from this point to this point. Okay? And the walls that actually can cover the view is the ones that are closer to the origin point than the point that we are trying to view. Okay? So to simplify things further, let's assume this is 0, 0. So basically for each point we translate the whole problem to make the origin, the actual origin, so it's easier for the math. So now we want to know if the distance to this point is less than the distance, but not any distance to the wall segments, but the distance on this direction to the active walls. Okay? We want to know if there's a wall that is closer on this direction to this point than this point is. Okay? The good thing is that since the walls do not cross, the closest wall is always the same until it disappears. So if this wall is closer than this wall over this line, then it's also going to be closer over this line. Right? They cannot swap places, because if they swap places, that means that by a continuity argument, that means that at some point they were crossing each other. Right? Because the distance, as we move this line, the distance to a given wall is a linear function. Sorry, a continuous function. Okay? And the difference between two continuous functions is a continuous function. So if the sign of this continuous function changes over time, that means it was 0 at some point, which means if the distance of both in the given direction was the same, that means that both walls cross at that point. Okay? So this is a simple continuity argument, and this is really good because then we can maintain the walls ordered by distance to the origin. Because what we really want is, okay, what is the closest wall? Right? Because only the closest is the one that, I mean, if some wall is going to cover the view, then the closest is going to cover the view. Because we said that we only care about comparing distances. So of course, if we compare the shortest of these distances, then if that is not short enough, then all the others are not going to be short. And if this is short enough, well, who cares about the others? Right? But okay, so we need to maintain the minimum. So which is the closest active wall? And then we compare the distance to this active wall with the distance to the point. But this minimum, so the thing is that to maintain it, this is a regular trick that appears a lot, right? To maintain the minimum, we actually need to maintain a total order among the things that are active. Why? Because, well, when the minimum disappears, we need to know, okay, now we need the second minimum that has become the actual minimum, right? So if we didn't memorize anything about the second minimum, now we have to go search it with brute force. Okay? This is a typical trick, not only in geometry, also for some dynamic programming problems, in which we only care about minimum or maximum, but we need to maintain the order all the time to be able to update this. Okay, so what we do is we maintain the order such that when this line passes through here, and we say, oh, this wall disappeared, this one, which was the second minimum, now becomes the new minimum, and the new distance we use to compare for the next point we got. Okay? So we need to maintain. So this is similar as in the all segments intersection algorithm. We are always maintaining the current segment ordered by y coordinate if we are moving horizontally, or by x coordinate if we are moving vertically. In this case, we are sorting by distance to the origin. Okay, distance, once again, in the sense of distance in this direction, over this line. Okay? Okay, so we need to do so what are the stop points of this rotating line? Sometimes we have to do some queries when we encounter a point. We have to check the current status to decide whether this point we encounter we can see it or not. And sometimes when we encounter an endpoint of a wall, we have to alter that structure. We have to either add a new wall to the active walls we are considering, or we have to remove a wall, depending which endpoint we encounter, or we have to insert a wall or remove a wall that is no longer active from here. And here comes the good part that since there is no collinearity, that means that we can perfectly order all the points and not worry about, okay, we are finding an endpoint of two walls at the same time, or an endpoint of a wall and a kid all at the same time, right? Because if that would happen, then those two together with the current origin we are considering will be collinear. So that is great. We don't need to worry about how to break that, which is usually one annoying thing to do in streamline algorithms. So what we do is we sort all the endpoints of all the walls and also all the points by angle according to this origin, and these are the points that our line. This is the order in which the sweep line are going to encounter the points along its way around. Okay. So we not really advance a floating point variable. We just iterate through the array of all the points sorted by angle. Right? And the angle of the current point is the angle of the current line. Right? So in this case, we will start, we will have this will be number 1 because we have 0 here. This will be number 1, this is going to be number 2, number 3, number 4, 5, 6, 7. Okay? As we rotate, we are countering the points in angle order. Okay. Sorting by angle is pretty easy, especially if you use N2. Do use this every time. Do not be unnecessary arithmetic. Also, one piece of advice: this is a really nice function. So set Google for it if you don't know it. It's really nice, but it's really slow. So if you are going to be calling it several times, many times you call it several times for the same points. Because you need the angle first to sort, and then you need the angle again. For instance, for sorting, you need the angle more than once, because you have n log n comparisons in total, and you only have n angles. Right? So it's better to memorize, if you're going to use several times the same angle, it's better to memorize the result of this function in some some variable called angle or something. Like, I don't know, you have point. A point that has interval. So I will just double here to store this value if you are going to use it several times because the function is not.
I tried to use the data to different contests, but I had a problem when, for example, I got like the 5 and 4 segment there. If I get 5 before, for example, if the order starts on 5, then I get the element for the 5 before the 4, and then I have to break the segment in 2.
Okay, that's just, yeah, so, yes, you not always start, yes, like what happened here with this one.
Is there a way that I don't have to do that?
Yes, I'm going to explain it to you. Yes, you definitely don't need, what you do need is to sort, to check each wall, to check each wall's angles to see whether you need to put them in one way or the other. I mean, you need to identify which is the start endpoint and the endpoint, and the finishing, right? So this will be starting and this will be ending, and this, in this case, this will be ending and this will be starting, right? But since each segment is always in only 2 quadrants and not, right? Each segment cannot really, so not 2 quadrants in the regular sense, but so there's each segment is completely contained in half of the plane according to this order, right? Because you can cut parallel to the segment. Okay. So yeah, there's an easy way to decide which is the beginning or which is the end, and if the beginning has a really large angle and the end has a really small angle, like in this case, then what you have to do is start with this point in the segment. In this segment is entered at the beginning. What I usually do is just do the pass twice, and the first time don't consider the result. So when we start the second time, you're going to have the set with all the active walls that start acting. Okay, that's much better than breaking it into 2, because breaking it requires a lot of extra math that you already need for the rest of the process. But let's get to that later. So we're going to be encountering this point, and we're going to be wanting to maintain the set of active walls ordered by distance to the origin. Okay? So since I already proved that the distance cannot change over time, and the distance can change, but the relative order of active walls cannot change over time. Okay, we can use the standard library set to maintain this. So we have something like a set of wall or segment, or okay, with a special comparison function that compares 2 walls according to their distance to the origin. Okay? This is strange, right? Because this is a value that changes. So because it depends, so it compares by the distance on a given angle, right? We have some current angle, right? And the set compares according to this variable, the current angle of the line, right? So this is something that you cannot always do, because if you change the comparison in the middle of the process, then the invariance inside the red flag tree or the tree that makes the set can be broken, right? But as we showed, they are not broken because the relative order of active walls never changes. Okay? So since all the invariance depends on comparisons, and all the comparisons do not change when we change the angle, right? As long as the set only contains really active walls, because other comparisons may change, but the active walls don't change. Really, the set is going to work, and we will have the minimum at the begin iterator and the maximum at the n-1 iterator, and all the good things about the set. Okay? Okay, the good thing about the set is that for free we can get insertion and removal all in logarithmic time. Right? You only have to adjust the comparison. Right? So when we get to beginning end point of a wall, we add the wall to the set. When we reach the finishing end point of a wall, we remove the wall from the set. This is the same as you do for sweep line segment intersection. Right? So it's only a different comparison function. Okay? And the comparison, I mean the distance, the only really difficult math part is calculating the distance from a point to a segment at a given angle. But it's just a little bit of trigonometry. It's not that hard, but it requires a little bit of math and paper. So we have this set, and whenever we encounter a point, we take the begin iterator, which gives us the least element of the set. By least, I mean the closest one, with the shortest distance. And then we compare that distance with the distance from the origin to the point we are checking. And if the distance to the point is less than the distance to the wall, then the point we can see, and we add one to some counter. And if not, then we do not add one, or we do not count that point because it's blocked. Okay? So this then the complexity of this, then first we need, so let's say n is k plus w, so it's the number of points total. Okay, so we have n log n time for sorting by angle, and then we have to do the sweep, which has n stops, 2 stops per wall and 1 stop per point. The stops in walls take logarithmic time because we either have to do an insertion or a deletion from the set, which either takes logarithmic time. And then the time on the points, it's linear because it's just a comparison between the minimum that we already know and the point. Okay, so in worst case it takes logarithmic time per stop, and we have n stops, so we have another n log n for the sweeping part. Okay, so the complexity is n log n overall. Okay, n log n means in this case k plus w. Is much better than k times tau. Okay? And in both cases, both this and this, we have to multiply by the number of seekers or number of points that we want to get a result. Okay? So the overall complexity of the solution for the whole problem will be s times k plus w times tau k plus w. Okay? So now a couple of things. For doing this, we need to know for each wall which point is going to be the starting point and which point is going to be the finishing point. Because we need to know when we stop at the point if we have to insert the wall or if we have to remove the wall. Okay? So, to do that, we just need to check the angles because the two angles, I mean, we need to check the order. So we check the angle for each of the points. Okay? And if the difference between if the largest minus if the big angle minus the small angle, right, is less than 180 or less than pi, okay, that means they are ordered correctly. So the minimum is the starting and the finishing is the ending point. Okay? Because when this happens, when the wall is like backwards, that means that the angle from the start to the finish is going to be like on the opposite side. Right? So it's going to have more than half a turn as an angle. And it can, right? If you think of any wall, the angle between this angle has to be less than 180. Right? So if you are seeing it be more than 180, that means you have the 2 points on the wrong order. So we can just stop. So we have to, it's important to adjust because to take every wall and adjust it at the beginning to have the points, to correctly identify the starting point and ending point. Okay? And the other thing is that when you start, you already have some active walls, possibly. The ones that have the starting point below being like some large number and the ending point being some small number. This can always happen. But there are two ways to go about it. Either you do first one pass over the walls to check if the wall has this property, then insert it at the beginning with the angle being 0. That's one possibility. Or a different, maybe a little bit easier, is to do 2 passes. So to do 2 sweeps. And in the first sweep, so in the first sweep what's going to happen is that you're going to encounter this and say, oh, I have to remove the wall, but the wall is not going to be there, but the set doesn't care, right? If you say remove for an element that is not there, or erase for an element that is not, then nothing happens, so it's fine, right? But on the first pass, we do not consider a result. So you do the first pass, and then you reset the counter, and then you do the second one. So but my actual solution for this problem has a from 1 to 2 to do 2 passes. And reset the counter in every pass, so only the result from the second pass that may be a little bit different because the second time we get here, this set of walls ends up with all the active walls that are active at the end, which are the same that should be active at the beginning. Right? Okay. Any other questions? So the other thing is that you have to be very careful when calculating this function, given a point and a segment and an angle. Calculate like this distance. This is needs a little math because you have a couple of cases. The general case doesn't work if the segment is either horizontal or vertical, depending on whether you do it on X or Y, and then you have to do like 3 cases. One when X is 0, one when the X coordinate is 0, one when Y coordinate is 0, and one other case for all the others. But neither is too difficult, just be prepared for some long math function to calculate. Okay, are there any questions, comments, or alternative solutions? Yes?
It's not necessarily compute the angle.
Which angle? Ah, the one for sorting? Yeah, you can sort with the comparison. You're saying how to do it? Oh, sure. Yeah. You can do angle comparison with integer a couple of your cross multiplication. Yeah, sorry. So my advice was not that this is the best way of since you are going to do floating point operations anyway, and there's no collinearity and everything. 8 and 2 is just faster to code. But talk to them. Not
swap the points and use one pass for that one.
So you start with the active. You insert at the beginning all the walls that need to be. Yeah, you can do.
Swap this first.
Yeah, sure, yeah.
Sure.
Okay. Anyone else? Okay. So let me comment briefly on the other geometry problems, the one remaining, so I can make some comments about the string problem. So the other geometry problem, the one with the platform lights, we have some box, we have some round columns, we have some points that emit light and are blocked by the columns. Right? And we want to know in the perimeter how much length in the perimeter is lit by at least one of the lights. By lit means that what is the measure of the length of the set of points in the perimeter that can be such that the segments from that point to some of the lights does not go through any of the columns. Okay? So for this, so let's first solve the problem for just one light. Okay? So this problem is, I like it because we have to do the same thing but several times. So we have one light and several columns. So what happens? Of course, if we consider the tangent through all the columns, these are the lines that separate light from dark. Okay? So it's similar to the sectors in the matrix that we talked about before with the electric problem. The status of the points on the border can only change from dark to light or from light to dark when passing through some of the lines. Okay, it's possible that it doesn't change. So we may have another one here. So when it passes this line or this line, it doesn't really change, right? Because all this part is dark. But these are the candidate points of changing from light to dark or from dark to light. Okay. So what we do is from each point. So there are several ways of doing this, of course. But from each point, we calculate the angle of all these lines. Okay? Because angles are easier to manage when you are looking at the rounding thing than actual vectors or coordinates. So we calculate the angle of this, the angle of this, and for each we know whether it starts covering. So this is a column start, this is a column ends, column starts, column ends. So we have a set of intervals of angles, right? Eventually, some column, since we have a fixed origin, some column may be like previously it was, maybe reversed. So we have like the starting be smaller than the ending. In that case, but in this case, since we only care about intervals, we can do what you said, that splitting the interval into two intervals. Like so we always have intervals properly sorted. So we calculate the set of intervals of angles of light covering, right? And then we calculate with the usual interval intersection or interval union in this case algorithm. We sort the intervals by its first coordinate or whatever, and then we take the union of all the intervals. We can do that in n log n time by sorting and then taking greedily. Okay, you know how to do this, right? About 3. And then we get a collection of intervals that represents the angles at which the light is covered. So if we take the complement, which is easy because it's just taking the endpoints of the intervals and reversing. So we take the right endpoint of the first interval up to the left endpoint of the second interval. That's the first interval of light. Okay? So we're complementing a collection of intervals in the 0, 360 or 0 to pi. It's easy. So those angles are the angles in which the light emits without being covered by any column. And then we can project all these angles into the walls. Right? We say, okay, at this angle, this is touching this wall or this wall or this wall. Okay, and we know that now we have intervals of walls, so we can do it for each wall individually because there are only 4 of them. So we have intervals of walls that are lit by this time. So if we do it for every light bulb, then we get for each wall, we get a set of intervals that are lit in the wall. So we need to take the union of all of these because it's possible that some part of the wall is lit by several. Okay, so again we have several sets of intervals and we need the union of all of them. So it's just the union of lots of intervals. We take the union and then we calculate how the length of a set of intervals, which is easy because it's just subtracting the right endpoint. Okay? So I'm sparing you all the math details of how to calculate this angle and how to project the angle to a wall. But then it's just if you draw and think about for a while, and you will. Okay. My suggestion is that you do that for several geometry problems, and then after 10 or 20, everyone is going to seem at least easy, and you will do it fast. So really, the whole difficulty for the problem is that the problem is really about one light and one circle, and all the rest is taking care of this union or intersection. Right? All the geometry is just one light and one column. Then to several columns is taking intersection, and to several lights is taking union. But both intersecting and taking union of sets of intervals is easy. Okay? Any questions? Okay. So let's try to say at least a couple of words about the string problems in the like 15 minutes we have left. So I'm going to talk about file retrieval because it's a little bit less technical. The other problems that I don't talk about, you can come ask me for hints or wherever now during lunch or whenever you see me not speaking here. Okay, so the problem is we are given several strings, and we are asked we have several up to 60 strings, up to 10,000 characters each, and up to 1 million characters in total. And we are asked, right? No. And we are asked to find which subsets of strings are searchable. When we search, we specify a string, and it matches every superstring of the string. So every string that contains the specified string as a subset. Okay? So the subset is searchable if it has some search string. So in order to do this, we want to operate with this substring, right? We want to know for some strings or for some interesting strings, which is the set of strings that it could match, right? We don't really need the strings as the sets, but so what we do is we build the suffix array of the concatenation of all the words in it with some separating character. Okay? Everyone knows what suffix array is? Okay. If you don't, you can do it. Now there's plenty of information on the internet because it's become kind of standardized programming contest in the last couple of years. So the suffix array of the concatenation looks more or less like the suffix array, like the ordering of all the suffixes of all the words in the set we are concatenating, right? So if you have I know, hat and cat, and we put some separator in the middle. When we sort this, we are going to have, okay, first we are going to have a T, then we are going to have a T cat, then we are going to have cat, then we are going to have cat. And then we have T, and then we have T. Okay? So the idea is that we are going to use, when you have several words, we do the same, but we use all different separators. We use different separators. What we do is we use the same separator, but we consider it to be different from itself. Okay, we symbolically make it different. There are several ways to go about this, and you can also do suffix strings, suffix arrays, if you prefer. So this more or less, since we consider all the separators to be different, we more or less can forget about all these parts and just think that we have the suffixes of all the words sorted. Okay? So all the suffixes of all the words in the input. So this is basically more or less as putting all the suffixes of all the words in the input in a try. Right? Because we have them sorted and more or less. And then this is the suffix. And then we build what is called the longest common prefix array. Which tells us for any two consecutive of these, how long is the common prefix between them. So between these two, between these two, 0, 0, 0, 1. Okay? So now with the help of the LCP array, then this really looks like a try, because we have the things sorted lexicographically, and we also have how much prefix in common two consecutive ones have. So this will be like the height of the first branching node in the tree. Well, in this case it will not be branching because those two are equal. This will be like, you understand? So this is so the bad thing is that it's not as comfortable to think about things as the trie or as a tree in general. But it's much easier to build. The algorithm to build this is much easier than the algorithm to build this in this tree form. But still, to think about the problem, we can think that we have all the suffixes in a trie. Okay? So suppose we do this. So we have a regular trie with words in it, and we have inserted all the suffixes of all the words in the input in the trie. So what means for a subset to be searchable? That means that, so for example, there has to exist some substring that matches exactly the words in the substring. And a substring is a prefix of a suffix, right? And if the suffixes are in a trie, then the prefix of the suffix is some path in the trie, right? If the suffix comes up to here, if we only take the path up to here, this is a substring of substring. Okay? So now for each node in the trie, we can think about which of the input strings, the 60 input strings, have at least one suffix that passes through the node. Okay? If a string has a suffix that passes through a node in the trie, that means that this substring matches that string, that the original string in the input. Okay? Because there's a prefix of a suffix of the string in the input that matches in the search. Okay? So each node represents a possible search, right? Because all the substrings, all the non-empty possible searches are represented exactly by one node. Because all the prefixes of the suffixes, so all the substrings are represented by a node. The things that are not substrings or of any string in the input, we don't care because they are not going to match anything. Okay? So each possible search is represented by one node in this chart. Then this is nice to think about this problem. Then I'm going to translate it back to the array. So, and then it's easy to calculate the set. So since there are only 60 words in the input, we can represent the set by the binary word, like a bit vector, or a long variable. And then it's easy to make unions and intersections. So each time we insert a suffix, you can add to the set that are already on the node. You can add the current word to that set, and then we have already all the subsets. It's possible that some subset is represented in more than one node. So we take a set of long or a set of p vectors to count how many different ones we have. Okay? So by putting the suffixes of all the words in a trie, it's easy to solve. It's more or less easy to solve the problem. So now, how can we translate this idea to here? So now, a node in the trie is represented by a consecutive part of this array, right? It's the consecutive part. So we have this is a suffix, this is a suffix, this is a suffix. Okay, so these three suffixes have, since they are all below some subtree, they have to all appear consecutively in the lexicographic order. Okay? So each node is a consecutive part of this array. Moreover, all the things that are below this are all the things that start with, let's say this is 80. Okay? Are everything that starts with 80. So it has to appear consecutively here, and also it has to appear with all the LCP values being 2 or more, because everything starts with 80, possibly more, but at least 80. Okay? So each possible substring in this view is represented by a consecutive part of here that has all LCP greater than some value. And it cannot be 0 because 0 is the empty string and we cannot search with the empty string. Okay? So this is not a good example, but let's say that if the LCP is like, let's say the LCP is like this, I'm not really writing the suffixes, then we could say, okay, we can take all these consecutive parts and consider length 1. Okay? And we can take all these consecutive parts and consider length 2, because all these are greater than or equal to 2. Or we can consider this part and consider length 3, or this part length 1, this part length 2. Okay, so we care about maximal consecutive parts that have all less LCP greater than some particular number. Okay? And the good thing is that there are only n log n many of these intervals. It's actually there at most n of these intervals. Why? Because, so what happens here is, let's start with the whole interval. Okay, that's one possible maximal interval. It doesn't work because it has a 0, but and then it's going to be partitioned by the zeros into subintervals. Right? All these subintervals are also maximal. Right? We partition by all the zeros. Then we partition by all the ones. Then we get smaller. Then we partition by all the twos. Okay? So this is something like a tree of intervals. We have the full interval, then it has as child some interval partitions by the only zero in the LCP. Then each of these is partitioned into by ones. Okay, and this is all the maximum. And since each value in the LCP partitions only once, then the number of branching of this tree is linear. Okay, so the number of nodes on the tree is linear. It's actually not more than 2n. Okay, so there are not many intervals, so not many subsets. Okay, so now the only problem remaining is how do we find them? Okay, so there are several ways to find the maximal subarrays here that are greater than or equal to one value. One possibility is to sort this by value and then insert into a set. Okay, so first we have the empty set, we represent the whole interval because there's no partition. Then we insert all the zeros. Okay, and then the query within the set is for a given position, give me the first element that is less than something and the first element that is greater than something. Okay, and then we discover an interval. Okay, and that way we can discover all these intervals. And also, the easiest way to proceed is if we put the segment tree on top of this with range limiting query, we can get for each of the intervals which is the appropriate length. Sorry, for each of the intervals, which is the union of the set. So each position here belongs to one of the words. So this belongs to cat, 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 this belongs to cat. Okay, so the subset of that position alone is just that word. Then when we take a consecutive part, the set is the union of all the sets in the range. And since union is an associative function, we can do like range minimum query, but do range union query. Since we have the sets represented by big vectors, we can do the operation efficiently. The union operation is just an OR. Okay? And for any consecutive range, we can know the union of that range as a set. So then for all these intervals we discovered, I know I'm going fast, but it's just a hint that try to remake it by yourselves. For each of these we can calculate what set it represents, and then that gives us a possible searchable set. And then for all these sets we discover, because each of these represent a node, right? A node in our track. Okay? So this is a set, and as we did here, we take all these bit vectors representing sets and we eliminate the duplicates, like putting them inside the set of log or a set of bit vectors. And then we just count how many of them there are. Okay? I hope this at least gives a hint for the ones that didn't have an idea how to solve the problem. This part of the segment tree can be simplified because as we build this tree is actually, it's not really the segment tree because but it's kind of a segment tree. Right? In the sense that each thing is a partition of its part. So, okay? So we can consider this to be the segment tree instead of building a binary tree to be the segment tree, and then use the same tree to discover the intervals and to calculate the union. We can calculate the unions as we discover the intervals. So we start with the whole thing, and when so we partition the intervals, and then when we come back from the partitioning, we take this, we take the set from this and the set from this, and the unit is the set from the part. Okay? So basically, what I said about the segment tree, which is easier to think about in a library way, we can just do it directly on this tree that we use. This is we don't need to build the tree; it's just a way to think about it. Okay. There's a problem in top coder called building arbitraries. I'm the author, so if it's not exactly this name, you can just find a problem written by Sonnen. It's old, but it's more or less this part of the problem. It's just using this kind of segment tree to find these maximal intervals and then doing some extra one. So if you want to get the problem, maybe it's a good idea to try this first to practice this small part of the problem before getting to the whole thing. Okay. Are there any questions in the last 2 minutes? Okay, so let's go eat. Sorry, I have a comment for tomorrow, this afternoon contest. So remember that we're going to use the problems you submitted, and since, of course, there wasn't as much time to develop the problems and test and everything as we do in an actual contest, it's possible that the text of the problems is not as clear or as nice as you are used to from an actual contest that we take 2 months to review the text. So as much as I deal with, I'm going to be a little bit. I'm going to try to be more nicer to you by answering questions about the statement, in case the text is not, because the texts are not as clear as they should. And also, the test cases and everything, I'm not sure how much each of the team that submitted the problems tested the test cases. So maybe, so don't try to solve the problems but with an idea that you know is not right, because it's possible that this data is not as good as it should be, so you get it with a flow solution or with a heuristic or something. I'm not sure because I don't really know. I just know that the test data, I just checked that the test data is more or less correct, so an acceptable solution will not fail. But I mean, remember that you're training and there's no really. It's not like in a contest when you say, okay, I have no other idea, no other problem to solve, I will just try anything. The important thing is that you think about the problem and just submit when you think the problem is actually correct. Okay?